Development of ultramicroelectrode stimulation. My name is Elizabeth Su, and I am a bioengineering and neuroscience major at Syracuse University. This summer, I worked with the Neuroprostheses Lab at UF under Dr. Kevin Otto, and my mentor was Elizabeth Olivo. At the Neuroprostheses Lab, I worked on developing ultramicroelectrode arrays. First off, what are microelectrodes? They are tiny electrodes used in the brain to sample recordings from and stimulate individual neurons. They've been in use for many years to get a better understanding of how stimulating different areas of the brain produce different effects. The problem is they cannot be implemented long-term in the body due to the foreign body response. During the foreign body response, devices are encapsulated by cells, which leads to the formation of a glial scar. This glial scar not only decreases the lifespan of the device, but also decreases the efficiency by increasing the impedance. Impedance is essentially resistance, and increased impedance means that less current can flow through the electrode. The solution we are working on is to make ultramicroelectrode arrays, or UMEAs, which are smaller than the neuron somas in order to decrease the foreign body response. By decreasing the foreign body response, we can increase long-term recording stability and enhance biocompatibility. Our project so far has three aims. Aim 1 focuses on modeling the characteristics, sizes, and shapes of the electrodes in the ultramicroelectrode array. Aim 2 focuses on acute surgeries in rats that are primarily for gathering data. And Aim 3 focuses on chronic implantation surgeries in vivo to determine long-term compatibility and functionality. So what exactly did I do? I primarily worked on aims 2 and 3. For aim 3, because our project is relatively new, as in we just finished our first year, we haven't had an opportunity to run chronic in vivo experiments yet. However, I've taught behavior to rats to prepare for these chronic experiments. I've been teaching them conditioning avoidance behavior using water and auditory stimulation. In this behavior, water-deprived rats drink from a spout that is connected to recording devices. When we play a certain sound, rats must learn to stop drinking. If they don't, they are mildly shocked. This does not hurt them. The goal for behavior is to test if the UMEAs are effective once implanted. Once usable UMEAs are produced, they will be implemented in the trained rats and used to stimulate part of the brain used to play that noise. If the rat can hear and stop drinking, we know that the UMEA works. My work for AIM 2 primarily revolved around EIS. So with the electrodes themselves, we are on our first generation or G1 design of the UMEAs. This G1 design features 32 electrodes with diameters ranging from 5 micrometers to 50 micrometers and was covered in sputtered iridium oxide film or SIROF. I've been testing them in vitro using electrochemical impedance spectroscopy, EIS, which is a technique that involves applying a small amplitude stimulus to an interface and then measuring the resulting output to characterize its properties. In this case, we were using EIS to characterize the degradation of the electrode and its SIROF film in vitro. Looking ahead, I'm planning to present my research at the 2023 BMES conference alongside my mentor, so I'll be seeing the NPR lab again in October. I'm also planning to apply to PhD programs in computational neuroscience this fall. Finally, I want to finish out senior year strong. My experience with SURF. I've had the most amazing time with SURF. I had so much fun meeting new people and traveling to new places. UF is such a big campus with so much to offer, and there's so much good food around Gainesville. I also made some lifelong friendships here. I value each and every one of the connections I had and would 100% recommend this experience. Thank you.